Hey, what's up, everyone? I hope you're all having a great weekend so far. Hopefully, the weekend stays as sunny as it currently is, because I certainly do want to make the most out of it. But anyway, I thought I'd go ahead and make this video on PicoTitan. So, I've talked about PicoTitan briefly in some of the Xbox 360 modding discords, like the Xbox 360 Hub, and I've also teased some of its features and functionalities, but definitely not the full set. So it's still got a long way to go to get to the point where I want it to be, but it's currently in the position where I'm quite happy with its capabilities, and I do want to demonstrate some of them today. So I've been spending 14, 15 months developing Pico Titan, on and off that is. I've been working on a lot of other projects as well. But essentially what Pico Titan is it's a complete re-implementation of the IBM Titan card. Now, if you don't know what the IBM Titan card is, I'm hoping to have a part one of my reverse engineering the Titan series up on my blog, so please check that out. If it's not up there, then check out xenolibrary.com for some preliminary information of Titan and how it operates. But essentially, Titan was a bring up card used to power on reset Shiva and the Waternoose DD 1.0 CPUs. These are prototype CPUs that were used during development of the Xbox 360. But my focus is actually going to be on the more well-known aspect to Titan, really the Titan version 2, which was used to bring up the Waternoose DD 1.0 prototype CPUs, which were used in the XEDK-1 systems. So Pico Titan, in its simplest form, is a re-implementation of exactly how the Titan 2 works. So it can step through the power and reset sequencer of a DD 1.0 CPU and apply the FSB PHY fixes, which was the main primary issue with DD 1.0 CPUs. And so it continues through the POR engine and applies these changes, and then goes to S reset so that the cores are online and jump to the reset vector, which is the 1BL. So that's essentially what the overview of the Pico Titan is, and I will go ahead and demonstrate that shortly. But it's very simple in terms of its hardware. As you can see, considering its name, Pico Titan, it's based on the RP2040, and it's also got a respective EEPROM to match with that, as well as a LED driver shift register, and a level shifter to shift the 1.8 logic level of CPU JTAG to the 3.3 volt level that I can use with the RP2040. So I'm going to go ahead and demonstrate PicoTitan booting up a DD 1.0 base system. So let's do it. So this is my DD1 lab system. Now it's basically a final retail motherboard that has been converted with a DD 1.0 prototype CPU. So it's also had the relevant board changes to allow that. You'll also see that I have added some indicator LEDs so I know what the SMC is doing, as well as the 5-volt rail and also the CPU check stop, which is behind the fan shroud. So this is called a Franken CDK. Now this is something that my good friend Josh Davison figured out how to do, and how to convert a retail fabbed motherboard into a XEDK-1 system essentially. So this also means that the board is set up with the relevant sysconfig strapping to allow me to intervene with the POR engine of the CPU via JTAG, and this is actually required for the Titan to work anyway. So you'll see this in the DD2.1, or sorry, DD2 to DD1 guide, which is on xenolibrary.com if you do want to do this conversion yourself. So you'll see that I've already got PicoTitan hooked up to this motherboard. Now, the top cable is the CPU JTAG, which is going all the way back to the CPU JTAG header that's on the board right behind over here, as well as a 3.3 volt rail coming in from the vMem port circuit. Now, this is actually how the original Titan gets powered. However, on the retail final motherboard, the header in which you usually connect to is not located there. So to tap into the 3.3 from the vMem port circuit, we soldered to the south side of a ferrite bead right behind the RF board on the motherboard here. So it's all set up, ready to go. I've got power coming in, as you can see, as well as AV connector, so we can get some video output. So I've connected the video output of this console through a component to HDMI adapter into a cheap Chinese HDMI capture device, so you can go ahead and see the system boot. Now it's going to boot the pre-release 1838 kernel, and one of the things that make DD 1.0 especially interesting to people is that you can boot even earlier kernels than that, and it's quite interesting to see the development of the Blaze dashboard through all of these different software versions. But anyway, as soon as I press that power button, what you're going to see is the PicoTitan is going to light up its 5 blue LEDs on the top. Pretty much exactly how the real Titan works. Now, PicoTitan can also display the status codes in case there's an error during the power and reset stages. But hopefully in this case we don't get that, and you'll see that pretty quickly the PicoTitan will just light up all 5 blue LEDs and then proceed to do the Knight Rider kit scanning animation, which is what's seen on the later versions of the Titan 2 firmware. So, because of some changes I've done recently to the firmware of the PicoTitan, it does take a little bit of time before it kicks in when I press that power button versus the original Titan, but that's just a small software issue I've accidentally introduced during the PicoTitan initialization, and I will be fixing that fairly soon. But anyway, let's go ahead and boot this system up. So like I said, as soon as I press that power button, you're going to see the PicoTitan will light up 5 blue LEDs fairly quickly, within a couple of seconds. Now, usually it'll be less than a second, but again, I will be fixing that. But as soon as those 5 blue LEDs light up, we know that the CPU has gone through the POR engine, hit the S reset, cores are online, and it's pointing towards the reset vector and has continued to boot the 1BL and the entire boot chain. So let's go ahead and do that. So here we go. There you go. You see the lights have lit up and the green LED on PicoTitan says, yes, we're good. And hopefully you'll see, there we go, the boot animation on the Ring of Light and also the boot animation on the console. And there we go. You'll see 2.0.1838.1 beta and also the name of the system, which is Warnoose 1 Lab System. So there we go, that's the DD 1.0 system booting up with PicoTitan. So in terms of power and reset in the DD 1.0 based CPUs, PicoTitan has actually been able to do this for over a year now, and is one of the very first things I achieved with this project. However, I decided I wanted to take this much further and add the more advanced features as well as add support for other CPUs to make things more interesting. So you'll see there's quite a lot going on the screen currently. The most notable thing probably being the PicoTitan application right here. Now this is what really takes PicoTitan to a whole new level, because it really just gives you that software abstraction to be able to interface with CPU JTAG and basically do whatever you want. Now you'll see down the bottom left on the camera that I have PicoTitan hooked up via USB-C all the way to the PC. And you'll see the console's not on at the moment, but the PicoTitan is in its USB debugging mode. And you'll see via the software up here that it says that PicoTitan is connected. Now you'll see just on the overview here of the PicoTitan application that we have the functions on the right hand side, which give you basic functions like powering the system on and off, as well as POR based functionality like resetting the POR engine, entering the POR mode, which is what is used by default by PicoTitan when the USB-C cable is not connected, as well as things like sending JTAG instructions and basic MMIO access via within the CPU silicon. So on the left hand side you'll see all of this information that can get populated. This is populated once the POR engine has completed and the system has started its boot sequence. Now some of this information being the JTAG ID code, as well as the CPU ECID information. It also pulls in postcode information, so the last postcode, as well as all of the information inside the POR status register, as well as some power management information like the CPU VID, which is quite useful. Now, I wanted to take this a little bit further and make it act even more like something like an IBM RISC-Watch, which is something that was used with the Xbox 360, which is a processor probe, and added in this small scripting engine. So it's kind of based off how the IBM RISC-Watch scripts work. It's just my own kind of take and my own implementation. So we can go ahead right now and boot up the system, by using the scripting engine. Now I've written a script, but I'm just going to exec it this way. So my script is a POR PicoTitan script, and I'm going to pull in my own PLL configuration data as well as my own configuring data. So I'm going to use the stock configuration ring for DD 1.0 CPU. Now this is the default configuring that is sent with a Titan 2 usually. And then this PLL config is a slightly modified PLL config, which is going to clock the CPU core clock to 3.2 GHz. Now, DD 1.0 usually runs at 2.8 GHz, so this is actually an overclock. So if I go ahead and click run here, you'll see that it says task 1 waiting for JTAG, okay? So, of course, the CPU is not, the system's not booting currently, right? It's turned off. So you'll see that the PicoTitan has also set one of its LEDs to 1. Now, what we can go ahead and do now is I can click console on, and you'll see the console booted, you'll see the LEDs went, and you'll see that all the steps completed, and there you go, you'll see the system has booted at 3.2 GHz. So if we switch back to the overview page, you'll see that all of this information has now been populated. So if we go and look at the ID code information, you'll see that we have the model as Waternoose DD 1.0, as well as the ID code of the tap controller, the manufacturer, and the silicon revision, which is 0 in this case because it is a prototype CPU. Now you'll also see the ECID information, which is pulled from the manufacturer and eFuses, has been populated. So you'll see that the wafer ID is here, which is unique to my specific CPU, as well as the wafer offset, which is the offset in which the die was actually cut out of the wafer. So you'll see the fabrication facility, the assembly facility, the TDP, which is unknown. I believe this was never blown into these prototype CPUs, and that's why it's unknown, as well as the chip revision, which is, again, DD 1.0. So you'll see over here we have the POR status information as well, which shows that the CPU is in an unsecure state. The POR status, the last POR status is this, which is S reset. And you'll see if check stop has been enabled and, the PLL locks as well. Now you also see down here in the bottom left the PMC information. So this tells us all the VID information. Now you'll see power up VID is 1.1425 volts. So this is the VID that is applied before the POR engine has set up and read in its VID from the manufacturing fuses. And this low power VID is the actual VID that is set once the console is running. Now there's also VID deltas that can be set by the SMC, and it's in the SMC config blocks, but I'm not going to talk about that. But yeah, and you'll also see on the right side here, the postcode is showing as well, the last postcode being 0x72. Now for 1838, 0x72 is the last postcode. You'll probably know, if you've messed around with 360s at least and diagnosed, that the last postcode that's usually spat out of a retail system is 0x79. So slight differences in the postcodes. So if we go to the scripts over here, let's clear this. We can go ahead and load in another script I wrote, which is to dump the OTP1 fuses. So if we go ahead and clear the console box down here, we can go ahead and use MMIO to dump all the fuse sets. And if we go ahead and do that, there we go. You'll see down here we have the fuse set of DD 1.0, which is actually all zeros. They never use these OTP1 fuses, not even for 1 bit, which I found quite interesting. So I've gone ahead and switched out my DD 1.0 lab system with this DD 2.1 lab system. Now it's hard to see, but essentially all this is a Xenon 0 fuse. Now a Xenon 0 fuse, because it's a 0 fuse, it means the CPU is in an unsecured state. And because of that, I was able to change the strapping resistors of sysconfig in the same configuration as the DD1 system so that I could use PicoTitan to intervene with the POR engine of this CPU. So I'm going to go ahead and use the same POR script I wrote for DD 1.0, and in fact we're going to use the exact same data that Titan 2 uses to bring up DD1, and we're going to use that on the DD2 as well. Now, of course, this data is outdated and is not the exact same configuration that is on the CPU, but that doesn't really matter for my testing currently, and I do have dumps of this information for this particular CPU. So let's go ahead and click run. You'll see again it says the task, the POR task. So I'm going to go ahead and power up the system. Now this system just has a DevGL 17559 image on there, so you'll see once it boots, there we go, it boots into that image. Now if we go back to the other tab over here, the overview tab again, you'll see it's updated again, and now we have the information for this CPU. So it's a Waters DD 2.0, again it says IBM, and you'll see that Silicon Revision is now 1. You'll also see new ECID information telling us that the TDP is 85 watts, and you'll see all of this is different as well because it's a different CPU. You'll also see that the specific chip version is a DD 2.1, okay, so it has a minor revision change. And you'll also see that the POR status information is basically the same, but you will see that the PMC information is slightly different, and you'll see the stock VID that the CPU runs is 1.3300 volts, which is quite a bit more than the default DD 1.0 configuration data. And again, you'll see the postcode is now 0x79 because we're on the later kernel. So we can actually go ahead and dump the fuses again of this system, the OTP1 fuses that is, and you'll see that they're still 0 because this is a 0 fuse CPU, but you'll see that it starts with the C0000. So let's try something different. So this is a different POR script which is based off of the previous script we've been using at this point, which is then based off how the Titan 2 boots up Waternoose 1. Now, the differences are, instead of me scanning in a PLL config during that boot, we are actually going to scan in the entire manufacturing eFuses, which gives us not just control over the PLL config, but also the VCID information and the VID, which you can see here. So this data here is going to clock the CPU at 3.4 gigahertz, which is a slight overclock, as well as a VID of 1.2550 volts. So let's go ahead, let's run this, and let's power up the system. So there we go, you'll see it's handshake. If we go over here, you'll see the postcode, but it's not updated. Let's refresh, there we go. And the system is booted. Now what you can see is the ECID information is all incorrect, and it's because I've scanned in my own bits for this, and they are not correct currently. I still need to sort all of that out. But you'll also see under the PMC status that the VID low power is now 1.2550 volts. So the CPU is requesting that much voltage. Pretty cool. So yeah, that's PicoTitan. Now, PicoTitan isn't just limited by Waternoose based systems. Those just happen to be the systems I wanted to use in this video. Mainly because I wanted to demonstrate DD 1.0 being booted up by PicoTitan, just like how the Titan 2 does it. Now, it also supports low-key, as well as the XC GPU found on the Slims, and it also has limited support with the Obon CPU found on Winchester motherboards. However, I'm still trying to work out some of the quirks with that system. So of course you do need a zero fuse based system or a super dev kit, because those CPUs are in an unsecured state and allows PicoTitan to have unfettered access to the CPU. However, PicoTitan does actually work on secured systems with very limited functionality. This is because JTAG is not completely disabled on secure CPUs, so you can use PicoTitan on a retail system to either read postcodes or pretty much every other piece of information I showed you on the overview page of the PicoTitan software, bar a few little details. So I hope you enjoyed watching this video. Now, I wasn't able to cover everything I wanted to because, quite honestly, PicoTitan is one of those projects that just allow you to do whatever you want with the software. You know, with the use of the scripting engine, it allows you just to write your own scripts and do whatever you want. Now, if you wanted to, you could use the MMIO access to dump the 1BL or any other part of the secure ROM or any part of anything inside the CPU silicon for that matter. And I didn't show the access that you can also get on secure systems, but maybe I'll show that in another video. But yeah, I hope you enjoyed this, and yeah, thank you for watching.